The National Broadcasting Company, in cooperation with the Office of Civil and Defense Mobilization and the Educational Television and Radio Center, presents 10 for Survival, a series dedicated to man in the nuclear age. Today's program, The Unseen Enemy. Your host for the series, NBC's distinguished commentator, Chet Huntley.
Welcome to Program 7 in our series, 10 for Survival. This and the following two programs will be devoted to a study of the hard facts of nuclear war, with particular emphasis on the unseen enemy, radiation. In the past, the average citizen has seemed unwilling to open his mind to the harsh realities of this threat to his existence. Perhaps if you have been a faithful viewer of this series to date, your own attitude will have changed enough to persuade you to accept the information we're about to bring you. We hope so, because frightening though the facts may be, there is reassurance in them, and there is undeniable truth that as your knowledge of these things increases, so do your chances of survival if nuclear power were used to destroy millions of people. In other words, it's up to you. Our story begins in the pre-dawn hours of March 1st, 1954. A Japanese tuna trawler, Lucky Dragon No. 5, out of Yezu, Japan, was cruising some 70 miles east of Bikini Atoll in the Pacific. Suddenly, members of the 23-man crew said they saw the western sky light up with the light of 1,000 suns. But what they saw was Operation Bravo, the explosion of a 15-megaton bomb, a weapon equal to nearly 1,000 Hiroshima bombs. In one flash of light, an entire island disappeared. The mushroom cloud rose to a height of nearly 20 miles, and soon a fine grayish-white ash began to fall on the decks of the little trawler. The men of the crew were curious about this ash that had covered their clothing, their skin, and their hair, and one crew member even scooped up a bagful and kept it under his pillow that night. And although the sea was calm, the whole crew became seasick. Within 3 days, there was a swelling and reddening of their faces, their necks, and their hands. By this time, they began to suspect the ash, and they called it shinohai, the ashes of death. It was 2 weeks before the sick and frightened men made home port, and then the whole world suddenly knew that fallout from the Bravo bomb had very nearly killed 23 fishermen 70 miles from ground zero. From that moment, the world entered a new and terrifying age, the age of fallout. Here with us now are two experts on nuclear weapons and their effects. This is Dr. Frank Shelton, Technical Director of the Armed Forces Special Weapons Project, United States Department of Defense. And this is Dr. Lauriston S. Taylor, Chief of the Atomic and Radiation Physics Division, National Bureau of Standards. Mr. Taylor, how did the Bravo bomb differ from earlier atomic weapons?
Well, principally in the matter of size. Other than its size, there was nothing special about it to produce radiation. Radiation and its dangers were well known in scientific circles long before the March of 1954. Radiation was observed and recorded in the first atomic bomb ever detonated in the testing grounds in New Mexico. It was the presence of radiation in Hiroshima that told the Japanese scientists the nature of the huge force which had destroyed their city. But while the incident of the Lucky Dragon by no means ushered in the age of radiation peril, it did serve to focus the attention of the world on the magnitude of the threat. But to evaluate this threat and to find ways and means to protect ourselves against it, the first requisite is that we understand it. I can think of no better person to explain the nature of nuclear explosions than Dr. Frank Shelton.
Well, Dr. Shelton, could you give us an overall picture of the effects of nuclear weapons?
Well, Mr. Huntley, you could easily fill several volumes with data on these effects, but let's start by describing what happens when a nuclear weapon goes off. For our purposes, the discussion, we'll talk about two different sized bombs, a 20 kiloton bomb and a 20 megaton bomb. Kilo stands for 1,000, so that a 20 kiloton bomb means one with an energy of 20,000 tons of TNT. mega in the same way stands for million, so that a 20 megaton bomb means one within the energy of 20 million tons of TNT. Now, at the moment of a detonation, a tremendous amount of energy is released in a very small space and in an extremely short span of time. This rapid release of energy produces an immense heat of several hundred thousands of degrees. That's a great deal hotter than the temperature of the surface of the sun. These extreme temperatures produce a luminous sphere of hot gases, which we call the fireball. Some idea of the size of the fireball in a megaton range weapon can be gained from this picture, which shows the skyline of Manhattan in the same scale. Now, some of the enormous energy of the bomb is given off immediately as thermal radiant heat. Except in the matter of degree, it is no different than the heat produced when I light a match. As you see from the chart, about 35% of the total energy of the weapon is delivered in the form of thermal radiation. Another 50% of the energy goes in the formation of a blast or shock wave. I can produce a fairly mild shock wave by clapping my hands and knocking a piece of paper down, for instance. In the case of the bomb, the shock wave is caused by the expansion of the fireball. The air in front of the fireball is compressed into a dense front of air. This shock wave moves out radially in all directions, a very high energy, traveling about 900 miles an hour. One can gain some idea of the power when he thinks that a hurricane travels about maybe 100 miles an hour. The shock wave from the bomb moves 9 times as fast, and remember that the air is much more dense than the air in the hurricane, so that its destructive power is actually much more than 9 times as great. Another 5% of the total energy of the bomb is emitted within about the first minute in the form of initial nuclear radiation. The remaining 10% in the energy of the bomb is emitted as residual nuclear radiation, or as we call it, fallout, over a very long period of time. Now, as the fireball rises after the explosion, the gases cool rapidly and condense to a radioactive cloud, the familiar mushroom cloud. If the weapon is burst at or near the Earth's surfaces, a large amount of material, fragmented earth, rock, and so on, is sucked up into the column in the rising cloud. Since the temperatures are very high, this material is in the form of gas, just as water becomes steam when it is heated. These vapors rise higher and higher and cool and condense. As the condensation occurs, much of the material becomes radioactive. The heavier bits of this material fall back to Earth rather quickly. The lighter particles continue to rise with the cloud, and many of them may be carried long distances by the winds of the upper atmosphere. Some of them eventually falling to Earth hundreds of miles from ground zero. It is this material, of course, that we call fallout.
Well, now, a moment ago, Dr. Shelton, you mentioned some various types of radioactivity. Could you explain that now?
Well, you remember we said that 10% of the total energy of the bomb went into residual nuclear radiation, which appears as fallout. Exactly as in prompt radiation, this energy is expended by the emission of certain particles and rays. These are alpha particles, beta particles, and gamma rays. Alpha particles are relatively heavy. They're absorbed by passing through only a few inches of air, and their ability to penetrate materials is very slight. For instance, they do not even penetrate the outer unbroken human skin. They do not represent any particular great threat. Beta particles lose their energy much less rapidly than do the alpha particles, and so have a greater range. When in contact with skin, they produce beta burns. The crew of the Lucky Dragon suffered from these burns, but a small amount of mass is usually sufficient to protect against them. Heavy clothing, for example. They may be washed away with water to prevent damage to the skin. But gamma rays are quite another matter. They represent the greatest threat in fallout. They are very penetrating, and in fact, they act very much like the familiar X-rays. They penetrate fairly dense material without losing very much of their energy. For that reason, they can pass through clothing, the body itself, affecting the cells of any of the vital organs.
But just how long does this radioactivity last following a nuclear explosion?
All radioactivity decays or loses strength with time. This can best be illustrated with this diagram. If we take 100 to be the strength of the radiation 1 hour after the explosion, we can then chart the rate of decay. In 2 hours, the radiation will have dropped to about 1/2 of its original strength. After the first 7 hours, it will be to about 1/10 of the original value, or in 10 units on our chart. After 2 days, it will drop down to about 1 unit, or about 1/100th of its original strength. After 2 weeks, it turns out it's down to about 1,000th of its original value. We can carry it out this indefinitely. For instance, at the end of 2 weeks, it's down to a 10,000th of a unit, and so on.
Well, then, obviously, the danger from radiation is greatest in the first 2 hours following a nuclear blast.
Yes, exactly.
Well, Dr. Shelton, assuming that bombs are equal size, what influences the amount of fallout?
Well, the main difference in the production of fallout results from the point where the detonation occurs. That is, whether it's an air burst or a ground burst. The air burst is one in which the fireball at no time comes in contact with the Earth's surface. This means essentially that the local fallout is negligible. The radioactive fission products themselves are very light particles which are carried up in the rising cloud and would remain aloft for very long periods of time. By the time they reach the Earth's surface, they would have decayed, most of them, into harmless, inactive materials. But note that blast, thermal radiation, and the prompt initial radiation received by ground targets will be very hard to shield against. The bombs at Hiroshima and Nagasaki were, by the way, air bursts of this type.
I see, but now from your definition of an air burst, I imagine a ground burst doesn't necessarily have to occur right on the ground itself, does it?
That's correct. A surface burst is considered one in which the fireball does at some time touch the ground. In the case of the surface burst, the ground absorbs a lot of the heat, the blast, as well as this prompt radiation. However, there is a maximum of fallout in the surface burst because of the large number of particles which are sucked up in the column and the rising cloud which become radioactive. Also, a crater is formed in the vicinity of the burst, and the crater is highly radioactive.
Now, just how large is the crater produced by, let's say, a very large H-bomb?
Well, there is a bomb crater in the 20 megaton range, 1,000 times larger, for instance, than the bomb at Hiroshima. The crater is about 250 feet deep, and it's about 3,500 feet across. A 10-story building in the bottom of the crater would not reach the surface. And if we assume a direct hit on Times Square, the crater would reach from about 30th to 50th Streets and from about 11th Avenue to Lexington. So as you can see on the map, this is an area of some 500 or 600 city blocks.
Now then, Dr. Shelton, so far we haven't talked very much at all about what these things, heat waves and blast and nuclear radiation and all, do to people and inanimate objects.
Very well. Let's examine briefly some of the effects. The first effect to reach you, of course, is the flash or the thermal wave traveling at the speed of light. Following that comes the blast, spreading out in all directions from ground zero and moving about 900 miles an hour. Its primary effect, of course, is to damage or destroy buildings and other structures. The moving shock wave produces a crushing effect on the structure as it engulfs it. Here are different types of buildings built to test blast and thermal effects in a bomb test in Nevada. In each case, watch what happens. When the heat wave strikes, followed by the shock wave, now let's watch the frame house again. This is the frame house again in stop motion. Remember, all of this takes place in a little less than 3 seconds. Such structures as multi-story brick apartment houses are quite vulnerable to the blast wave. All such structures would be destroyed within a radius of about 8/10 of a mile from ground zero for a 20 kiloton weapon. That would be an area of perhaps 500 city blocks.
Well, now, what about a 20 megaton bomb? In how large an area would it destroy all such structures?
Such total blast destruction would include an area within a radius of about 7 miles from ground zero, or a total of some 150 square miles. Here's our map of Manhattan with the crater at ground zero. The area of total destruction would cover this area. You might take a map of your own town and draw a 7 miles radius, and that would give you a vivid idea of the area of total destruction by blast.
Well, that's certainly frightening enough, but now then, tell me, how would this blast wave affect people?
The human body is able to withstand rather tremendous pressures, so that the blast wave itself would produce few fatalities, but the secondary effects such as falling debris, flying glass, and even people themselves being thrown about would certainly produce a large number of casualties.
And how about then the heat wave from the bomb?
The heat or thermal waves cause the greatest damage by kindling fires. You'll remember from the film the almost instantaneous fire that started when the flash came. Any combustible material within the range of the heat wave will probably be ignited, and widespread fires could be expected to rage in the vicinity of the target. As for its effect on people, thermal effects from a nuclear explosion can cause severe or even fatal burns, depending upon the amount of exposure and the distance from ground zero. Dark-colored clothing absorbs the heat and produces burns far more readily than light-colored clothing, which tends to reflect the waves. For example, here are the burn marks on the back of the Hiroshima survivor. The skin is burnt in a pattern corresponding to the dark portions of the kimono worn at the time of the explosion. Any kind of shielding at all between a person and the source of the thermal radiation will act as a shield and prevent burns. Yet, in a 20 megaton explosion, unshielded people could be expected to receive third-degree burns, which are deep, scarring burns, and in many cases prove fatal, up to a distance of perhaps 20 miles from the point of the explosion.
Well, Doctor, are there measures you can take to protect yourself against thermal effects and blast?
Yes, a great many measures. Actually, anything you do to protect yourself against radiation, which we'll discuss in a minute, will protect you against blast and nuclear effects as well. If you had a little advanced warning and merely heard this siren from the civil defense, for instance, take cover warning, that is the wavering siren or the short bursts on the short blasts, you could probably very well save your life by acting quickly. From what we've just discussed, you can see that your main objective should be to crouch beside a wall or any other object that would shield you from the direct exposure to the flash. That would be the first effect to reach you. Your face should be covered and your eyes protected. The blast wave which would strike next could injure you in many ways. You should be, as far as possible, out of the range of flying glass. This and other objects hurtling through the air would be your greatest source of danger. Taking almost any kind of fairly adequate cover would greatly increase your chances of surviving blast and thermal effects.
Now, how about the effects of radiation? Merely taking cover from blast and thermal effects wouldn't protect you from that, would it?
No, except that any mass at all between you and the source of the radiation at least does some good in cutting down the amount of exposure. Here we have to distinguish between initial radiation and local residual radiation. Initial radiation is that which occurs within about a minute of the detonation. A 20 kiloton bomb, the Hiroshima size, would deliver a lethal dose of initial radiation within a range of about 8/10 of a mile from the point of the burst. That doesn't mean that everyone within that range would receive a lethal dose. However, persons with some shielding, just being inside of a house, for example, might cut the dose rate down to a considerable degree, might receive a dose low enough to permit them to survive in this region.
Well, now, Dr. Shelton, are those figures correct for the 20 megaton bomb? It would seem to me that they should be much larger.
Well, although a 20 megaton bomb is 1,000 times more powerful, the area that would receive lethal dose to initial radiation is not as great as you would imagine. The lethal range would be a little more than the 2 miles for the 20 megaton bomb.
But that's only what you call initial radiation. Now, what about this thing you call residual radiation or fallout?
Well, this phenomena is caused by the dirt from a surface burst being taken up into the fireball and the cloud, where some of it is vaporized together with the fission products of the bomb. As I've already explained, this produces radioactive particles of various sizes, which then proceed to fall out anywhere from ground zero to many hundreds of miles away, depending on the wind direction and velocity, the height of the cloud, and other factors. It would be possible to escape the effects of blast, thermal radiation, to avoid the lethal initial radiation, and still be killed much later by this residual radiation. However, there is one thing on your side: time. Having escaped thermal radiation, blast, and initial radiation, you may have an hour or more to find adequate shelter against fallout. Exactly how long you have to find the shelter depends, of course, on those many things. These would include how far you were from ground zero, how high the majority of the fission products have risen, the direction, the velocity of the wind, and so forth.
But as I understand it, gamma rays like X-rays are invisible. Now, how would you know that you were receiving fallout at some distance from a nuclear explosion?
Well, Mr. Taylor and his staff at the Bureau of Standards have been working for some time on this and the related problem of shielding against fallout. I'd like to ask him to answer the question for you.
I'll be glad to try, Dr. Shelton. The only sure way to recognize fallout is by the use of instruments to record the amount of radiation being received. We're going to go into this program fully 2 weeks from today. But to be very practical about it, if an H-bomb were dropped within several hundred miles of you, I am quite sure that you would know about it very quickly. If in that case you began to notice fine dust or powdery white ash sifting down from the sky, you would most certainly assume that it was fallout and that probably it was lethal.
And then what would you do in that event?
I'd get to a shelter just as fast as I could, and preferably it would be a shelter with just as much mass between me and the outside as I could find. For example, in the corner of a deep basement, which had no outside windows.
But now, what about the exposure you had already received?
Well, I would certainly discard my outer garments, and I'd wash thoroughly to remove any traces of radioactive particles that might have fallen on me. I'd do this just as quickly as I could, because the longer such particles remain close to you, the greater is your danger from them. Now, you will note that I emphasize quick action. That's because time is all important in dealing with exposure to radiation. If you shorten the time of your exposure, you lessen its degree. As Dr. Shelton has explained earlier, the strength of the radiation falls off rather rapidly with time. This means it is strongest in the first few hours following the explosion. If you can manage to avoid an excessive dose during those first few hours, you will have increased your chances of survival immeasurably.
Well, it would seem to me then that we might have three possible factors working in behalf of us in the event of a nuclear attack, namely time, as you just stressed, distance from ground zero or distance from the blast, and mass or protection around us, huh?
This is quite right. Now, all of these factors have been mentioned in the preceding discussion, but I think it's important to emphasize these. Take distance, for example. Radiation falls off rapidly with distance, the intensity of the radiation. The distance means that radioactive material in the air has to travel further before it can fall on you and before you have to seek shelter. This involves time. During this time that the radiation is traveling, it is losing its strength.
And then we found out that mass or protection certainly helps too.
This is right.
Thank you, Dr. Taylor and Dr. Shelton. Thank you for a most illuminating description of the mechanics of nuclear explosions. We've learned that nuclear explosions produce 4 different effects: thermal or heat waves, shock or blast waves, initial or prompt radiation, and residual radiation or fallout. We've learned something of the devastating effects of these phenomena on structures and on people, and we have seen how these effects differ according to the size of the bomb. I wish we had time to continue the discussion, for there are many phases of the problem which we haven't yet touched. We have still to go into the manner in which the degree of radiation is measured, how exposure to radiation affects the human body, and what steps can be taken to minimize these dangers. All of these matters, however, will be taken up in detail in the following 2 programs. Next week, Dr. Shields Warren, a foremost expert on the biological effects of radiation, will be with us to tell us more about the effects of radiation on the human body. And then 2 weeks from today, Mr. Taylor will return to tell us much more about the protective measures that must be taken in order to survive a nuclear attack. Now, because we feel that this subject matter is of such vital importance to every man and woman and child in this country, we've prepared a booklet in cooperation with the Office of Civil and Defense Mobilization, which contains, in addition to the information we have brought you, specific instructions on what to do to help you and your family to survive in the event of a nuclear attack. And you may have a copy of this booklet free merely by writing to 10 for Survival, Box CD, Battle Creek, Michigan. We hope you'll write for your copy. Next week, our program is entitled Radiation and the Body. Until then, goodbye.
Executive producer for 10 for Survival, Malcolm McGregor. Produced by Joel O'Brien. Directed by Linwood King and written by William Welch. Our guests today were Dr. Frank Shelton, Technical Director of the Armed Forces Special Weapons Project, United States Department of Defense, and Dr. Lauriston S. Taylor, Chief of the Atomic and Radiation Physics Division, National Bureau of Standards. Survival was produced for the Office of Civil and Defense Mobilization and the Educational Television and Radio Center. This has been an NBC production. This is National Educational Television.